Jai Hind and welcome to all. This is my 8th lecture of module 2 spectroscopic techniques and its application, and in this lecture I will give the idea of Raman spectroscopy. The references are same. Elementary organic spectroscopy by Y.R. Sharma, engineering chemistry by Shashi Chawla, industrial methods of chemical analysis by B.K. Sharma, and Wikipedia. So, this Raman spectroscopy basically it was given by the Sir C.V. Raman, and if we read this slide, then the birth 7th November 1888 till 20th November 1970. He won the Nobel Prize in 1930 for physics, and he discovered the Raman effect. Raman effect is totally different from other spectroscopy, because in normal spectroscopy we took the concept that on excitation the electron goes from lower to higher or higher to lower energy by absorption or emission of energy. It means either transmission or absorption will occur. But in this spectroscopy we consider the scattering process and by using the basically camera on the perpendicular direction, and then we find which type of phenomena occur. So, it is a type of spectroscopy which deals with the absorption, which deals not with the absorption of electromagnetic radiation, it deals with the scattering of light by the molecules. While in other spectroscopy, and which we have studied like in UV visible, in IR, and third in rotational, we study the basically the radiation, absorption of radiation and then transmittance, but in this we consider the scattering. So, in 1928 Sir C.V. Raman discovered that when a beam of monochromatic light was allowed to pass through some organic substances, the scattered light having some additional frequencies over and above that of incident frequency, and this is known as Raman effect. So, in this spectroscopy the energy levels of molecules are explored by examining the frequencies present in radiation scattered by the molecule. So, simple we can say, suppose this is a molecule, and when we irradiate this molecule of let energy h mu, or we can say photon, and 99% chances that either absorption or transmittance, but in case of 1%, if the scattering occur, so in this scattering again there are 3 possibilities. The first condition is if the scattered light, let the energy is h mu. So, scattered light here we take, if we take h mu and let the after scattering frequencies let mu dash. So, after scattering energy h mu dash is equal to incident light, then this type of condition or this type of scattering is called Rayleigh scattering. But the another condition is either the photon or light it absorb the energy or emit the energy, or we can say either the molecule it give the energy to photon or take the energy from the photon, then this type of condition either frequency it become less or frequency become more. So, if the initial intensity frequency, that is mu, is greater than a scattered frequency, then Stokes lines are occur, and if less, then anti-Stokes lines are appear. So, either Stokes lines or anti-Stokes lines, that is shifting, is termed as a Raman shifting. So, we can say the photons it can be scattered either elastically or inelastically. So, elastically means the collision is elastic, that is the scattered photon has same energy as the incident photon, and inelastically collision means the scattered photon has energy either less than or greater than that of incident photon. And the shifting is, let the initial intensity h mu plus E, and after scattering the let energy is this. So, the shifting, that is either mu minus mu dash or mu dash minus mu, which is approximately delta mu, is called Raman scattering. And if we take in approximately 10 to the power 7 photons, about 1 photon is taken inelastically collision. So, inelastic collision, again we take the condition, and suppose these are the energy level, vibration energy level, and if suppose excited electronic level, if electron goes from ground to excited level, then this phenomena is called phosphorescence or fluorescence. But in Raman spectrum, we consider a virtual energy state like this. This is the virtual energy state. So, in this, if the initial intensity is if the initial energy or incident photon is equal to scattered frequency, that is h mu is equal to h mu dash or h mu naught, then this is called Rayleigh scattering. And if the transition, although it is totally different phenomena, because in IR absorption, the absorption phenomena take place. It means if the energy is absorbed by the molecule and the transition occur in a vibrational energy level, then this is called absorption, IR absorption. But here we take after scattering, and after scattering, if the energy it become less, then it is called Stokes scattering. If the after scattering the energy become more, that is the energy given by the molecule, then that is called anti-Stokes scattering. And these two type of scattering, because of inelastic collision, it is called Raman scattering. So, please see these 3 diagram, and these 3 are very important. If somebody asks that write the theory of Raman spectroscopy, then we have to draw these 3 diagram. These are the energy states, this is virtual energy state, and this. Now, intensity of Raman lines. If we suppose we took the, what is the intensity of a Stokes or anti-Stokes line, or which have high energy at room intensity at room temperature, then we know that Stokes lines are caused by molecule of lower energy level. And when we do any problem of this Raman spectroscopy, please draw these type of figure or diagram in rough side, this like, and suppose if energy is less, then it is a Stokes, and if energy is more, then it is anti-Stokes, and this difference, this is delta nu. So, here we see that Stokes lines are start from ground or lower energy level, and which is more populated. So, initially at room temperature, the Stokes lines have more intensity of absorption, but on heating, since the kinetic energy increases, that is the more molecules will go from ground or low to higher energy level. So, in this condition, the intensity of anti-Stokes lines will be more. So, anti-Stokes lines are caused by molecule of higher energy level and which is comparatively less populated, but when we increase the temperature, the intensity of these anti-Stokes lines get increased. So, if we compare the Rayleigh, Stokes and anti-Stokes line, so the first point is scattering. We know that in Rayleigh it is elastic, while in Stokes and anti-Stokes it is inelastic. Now, second, energy transfer, because the energy after scattering remains same, so it is none, while in case of Stokes and anti-Stokes, after scattering, since the energy get decreased, so energy is transferred from photon to molecule, while in anti-Stokes lines molecule to photon. The effect of on molecule in Rayleigh none, while in Raman, that is in Stokes and anti-Stokes, the excitation of vibrations or rotation, or in this case the de-excitation of pre-excited vibrations or rotations. The effect on proton, in this case the change in direction, or but the wavelength becomes same or frequency becomes same, but in this case both case the frequency get or wavelength get changed. The probability of occurrence, Rayleigh scattering, in case of scattering it is common, but these two phenomena are rare or extremely rare. Now, what is the condition to be a Raman active? So, the condition to be a Raman active is that the molecule, in molecule there must be a periodic change in polarizability. Now, what is polarizability? The polarizability, let me take a H2 molecule like this, and since the both atoms are same and electronegativity is same, so shared electron will be there. But if we applied a electric field, initially static electric field, so in this case we see that this pair of electron, it will shift it towards opposite side. Here is a positive charge, positive, and here it is negative. So, the electron pair, it will shift it towards this. So, the shifting of electron pair, it may be a polarizability. So, when an electric field E is applied in a molecule, its charge distribution get distorted, and this induces a dipole moment mu in a molecule. And suppose if we apply a electric field not in parallel up to perpendicular direction like this, and this is a molecule. So, in this case we can imagine that the shifting of electron pair, it will be less as compared to this type of field which is parallel. So, here we see that this shifting or this polarity, it follow a elliptical order, and this is a major axis and this is the minor axis. Minor axis can show that the polarizability is more. So, here the ellipse is not like this, it is like this, and major axis, it means that the polarizability towards this axis is low. So, the magnitude of induced dipole moment, it varies linearly with the strength of the electric field, because here we can easily say that the distortion, it depends on electric field. So, mu is directly proportional to E, and proportionality if we emit, then mu is equal to alpha E. So, alpha is the basically polarization. So, the proportionality constant alpha, it is called polarizability of the molecule, and it is a measure how easy it is distorted the charge distribution of the molecule. Alpha depends on the direction of electric vector relative to the axis of the molecule. So, that is, it is a tensor quantity. So, in this lecture we took only static field. If we apply a dynamic field, then the value of this alpha, it get basically, it depends on direction also, but here we take only this type of case. So, the molecule, we can say that the molecule must be anisotropic. What is the meaning of anisotropic? That is different properties in different direction. So, here we can say that the different polarization in different direction. So, it must be anisotropically polarizable. Spherical molecules are isotropically polarizable. If we take the condition like this, a spherical molecule. So, here we see that the distortion in each direction is same, but here it should be anisotropic, and that is why elliptical, it form elliptical form order, and therefore, they do not have Raman rotational spectra. So, they do not have Raman rotational and it has Raman spectra. A linear molecules are anisotropically polarizable, and that is why they give a rotational Raman spectra. Even a molecule O2, N2, H2, which do not have a pure rotational spectrum, but they have Raman spectrum. So, here we also take the polarizability concept. When a molecule is subjected in a strong external electric field, but which is static, the field, that field will distort the molecule, and electron charge distribution to induce a small dipole moment which is proportional to the electric field. This. So, here we see that the dipole field is there and the molecule of the position of molecule is like this. So, here the polarizability it is maximum because the field is in direction of the molecule. But now the molecule is in condition this. So, here we see that the polarizability it get changed. So, it follow a which form? Sine form, that is a cyclic form. So, if E is a static field and it induce the dipole, it may interact with light of the normal manner and the transition can occur. However, if external field is due to some intense beam of light, then this is a second order process, and since light first creates the dipole and then interacts with it, so the transition created in the manner will be very weak, but it will be observable. Now, mutual exclusion principle, and this mutual exclusion principle is for centrosymmetric molecule, that is the molecule which have center of symmetry. So, for centrosymmetric molecule, if those type of vibration which are Raman active will be IR inactive, or we can say which are IR active will be Raman inactive. For example, H2O2 N2, these three molecules have center of symmetry and we know that they are IR inactive because their dipole moment does not change during vibration. So, as per the mutual exclusion principle, they will be Raman active. If we take a stretching of CO2, in case of CO2, stretching is symmetric. Symmetric means net dipole moment change 0, so it will be IR inactive, but it has center of symmetry. So, definitely this stretching will be Raman active. Now, asymmetric stretching of CO2, this. So, in this case, stretching towards the same direction. So, the change net change dipole moment. So, this stretching will be IR active. So, automatically it will be Raman inactive. But such type of molecules like N2O. In case of N2O, vibrations are IR active as well as Raman active. So, we can say this type of molecule does not have center of symmetry. So, this rule was very important to find or to predict the structure of compound. It means in case of N2O, when we consider the structure, so structure arrangement it may be like this or arrangement it may be like this. But since as per mutual exclusion principle, both vibrations are active, so it will not contain center of symmetry, that is this form will not be there. So, N2O it consists or it has this type of bonding, that is N bond N then bond with O. So, this in case of C2H2Cl2, so here if we took the transposition like this, so in trans there is a center of symmetry. So, if IR inactive, so Raman will be active. But in case of CH2Cl2 cis form, there is no center of symmetry. So, we will not apply this mutual exclusion rule. Now, next is pure rotational Raman spectra of diatomic molecule. Since in Raman spectra, on every rotation, that is full turn, the polarizability of molecule this return to its original initial value 2 times. So, in this case the selection rule will become delta G is equal to plus minus 2, where J is the rotational quantum number, while in case of rotational spectroscopy the selection rule is delta J is equal to plus minus 1, but in Raman we take twice, that is plus minus 2. For a rotational spectroscopy, we know that the energy is B into J plus 1. This centimeter inverse. So, if we want the change in energy or energy required for transition, so we can put a first label j and another label is j plus 2. And when we put the value of j as a j and j plus 2, then we get delta E or delta nu is B into 4j plus 6. That is, for a rotational energy level, these are the energy level, j is equal to 0, 1, 2, 3. So, in this case, for 0 to transition, the energy required is j is 0, that is 6B. For 1 to 3 transition, the energy required is J1, that is 10B. For 2 to next 4, we put J2, then it is 14B as per this. So, and delta J plus minus 2, it is one for Stokes line and another is for anti-Stokes line. So, we get this type of spectrum. So, at center, the energy of incident and the scattered is same, that is mu is equal to mu naught, and here negative side we get a Stokes line and here positive sign we get anti-Stokes line. The first line we observed at 6B and second we so 10B, 14B. So, we can say the spacing of line, first Stokes or first anti-Stokes line from the Rayleigh line is 6B. The value is same, but sign is different. So, because the formula is delta nu is equal to, or simple we can say the nu is equal to nu dash plus minus B 4j plus 6. So, we get the same value, but 6B minus 6B, 10B minus 10B. So, the spacing of first Stokes or anti-Stokes line is 6B, but after this it becomes 4B. Now, it comes 4B, 4B like this. And if we see the intensity order, then Stokes, Rayleigh and then anti-Stokes. Vibrational Raman spectra. So, in case of vibrational Raman spectra, the selection rule is delta mu is equal to plus minus 1. Again, plus minus is for the Stokes line and anti-Stokes lines. So, if we compare the Raman with IR, so first point is it is due to scattering of light in a by the vibrating of molecule, while IR it is the result of absorption of light. Second, the vibration is Raman active if there is a polarizability change, a periodic change in polarizability, while in case of IR the vibration is active when there is a change in dipole moment during vibration. In case of Raman, there is no need of permanent dipole moment, while in case of IR the molecule should have a change in dipole moment. Water can be used in a Raman spectroscopy as a solvent, but in case of IR water cannot be used, otherwise it will also show a intense absorption peak. In Raman, the sample preparation is not very elaborate, it can be in any state, we can take in solid, liquid and gaseous state, while in case generally solid or semi-liquid form is preferred, and gives an indication of covalent character in a molecule and it gives the indication of ionic character in a molecule. The cost of instrument is very high and it is comparatively inexpensive. Now, there are two questions on this Raman based, and when we solve question, please make this type of transition for Stokes and anti-Stokes line, that is suppose mu, it is mu dash, and this is suppose mu dash, this is for Stokes line and this is for anti-Stokes line, and this is delta nu. So, here we can say for Stokes mu dash minus delta nu, and for anti-Stokes mu is equal to mu dash plus delta mu, and here mu is equal to mu dash minus delta mu, just like this at the side. So, a sample was excited by 4358 angstrom of light line of mercury Raman line was observed at 4447 angstrom. So, calculate Raman shift. Generally, we prefer to give Raman shift in centimeter inverse. So, we avoid the calculation in angstrom, that is in terms of wavelength. First, we convert this angstrom into centimeter inverse, that is in terms of wave number. So, initial intensity or frequency is equal to 1 upon lambda. 1 upon lambda means 4358 into 10 to the power minus 8 centimeter inverse, which is equal to 22946 centimeter inverse. Now, the Raman line was observed, that is frequency of scattered light or wave number of scattered light, we can write S, which will equal to 1 upon 4447 into 10 to the power minus 8 centimeter inverse, which is equal to 222487 centimeter inverse. And calculate the Raman shifting. We know that Raman shifting is equal to nu plus minus nu dash. And here we see that if the initial frequency is more, that is 22946 is more than 22487, then the Stokes lines are appeared. So, here we see that mu initial is more than mu scattered. So, first answer is Stokes lines are appeared, and the answer is this minus this, and which is equal to, that is 22946 minus 22487 centimeter inverse, and which is equal to 459 centimeter inverse. Now, second and last question is, using radiation of wavelength 4000 angstrom, the first Stokes lines appear at spacing 350 centimeter inverse from the Rayleigh line. Calculate the frequency of anti-Stokes lines, and don't be confused in Stokes and anti-Stokes line. And when numerical, you start numerical at the corner or side, please draw like this, mu, mu dash, and this is delta mu. And we know that in Stokes and anti-Stokes lines, the shifting is same, but only sign different. So, wavelength using radiation. So, initially the frequency of initial, that is mu bar, is equal to 1 upon 4000 into 10 to the power minus 8 centimeter inverse, and which is equal to 25,000 centimeter inverse. And shifting is this, that is delta nu is equal to 350 centimeter inverse. So, first we find then what is the frequency of scattered light. So, in case of a Stokes line, we know that mu is equal to mu dash plus delta mu. From this diagram it is clear, I think. So, 25,000 minus delta mu is 350 centimeter inverse. So, this is basically frequency of scattered light, and which is equal to this. So, 25,000 minus 350, which is equal to 24,650 centimeter inverse. So, here we can find the scattered frequency of light. Now, in anti-Stokes line, we see that mu plus mu naught, and which is equal to this. So, in case of anti-Stokes line, what will be the frequency of mu is the initial intensity, which is 25,000 centimeter inverse, and the shifting is 350. So, here plus 350, and here we get 25,350 centimeter inverse. So, you can prepare these two type of question. First is this and second is this. Now, so here we finish this Raman spectroscopy, and this is in basically brief, and here we see only static field. Thank you.